Thank you for the invitation. It's great to be here. So I would like to describe some new algebraic constructions inspired by string topology. I will describe them in terms of Hochschild complexes of Frobenius algebras. I will define these from scratch. One of the main purposes is to state certain kind of duality for the free loop space of a manifold that resembles, in some way, Poincare duality for finite dimensional manifolds. Okay. The algebraic constructions that I will are also relevant to symplectic topology and mirror symmetry. In fact, what we will see today may be regarded as an algebraic theory analog to the Rabinovitz-Flower homology of the unit cotangent bundle of a manifold as studied by Alex, Chilibek, and Frunfelder. And in any case, I got to these algebraic constructions by studying string topology operations on chains on the free loop space of a manifold. So this is how I will motivate them today. Okay? And along the way, I will also mention some related and relevant work that I'm working with Dingyu, which concerns string topology at the chain level, but from a more geometric perspective. So this is kind of my short intro for what I will be presenting today. Okay? Good. So string topology concerns operations on the homology of the free loop space of a closed manifold. So M will be a closed manifold of dimension K. And we will have two main operations that will be relevant today. The first one is the first string topology operation, or the operation that gave birth to string topology, is the Chas-Sullivan loop product. This is an operation of degree minus k on the homology of the free loop space of a manifold. I will work over a field today, so we can take, let's take real coefficients for homology. So it's described by the following picture. Let's say we have a chain of loops in your manifold. And let's say we have another chain of loops. This is close to white. So the operation starts with two chains of loops, and we look at the projection of these so that those projections intersections versatile. I take the locus of intersection at the projection. I have a loop corresponding to every point in that locus of intersection, and I concatenate loops at that intersection. So I have a new loop. Maybe I can use screen. I have a new loop given by concatenating loops at every point in the intersection.
So you need to assume M differentiable.
Sorry?
You need to assume M differentiable.
Yes, M is a smooth manifold, differentiable smooth manifold.
And you really need it, you think?
No, later on one can prove that you only need a Poincare duality space. Okay, but for now, M will be, we can think of M as a closed manifold. Yes. So this is the picture for the Chas-Sullivan loop product. So maybe a bit more precisely, if I have chains in the free loop space, so I will think of a chain geometrically as having a domain, a manifold with corners. Okay, so let's say U is an I manifold with corners, and let's say V is a manifold with corners of dimension J. And the picture in terms of symbols is the following, given by the diagram. So you consider the projections of phi and C to M cross M. So this map is E0 is evaluation at 0. We can consider this map, and we want to intersect this map transversally with the diagonal. Okay? And assuming enough transversality, the inverse image of the diagonal along this map will be a manifold with corners of dimension I plus j minus k. And this will be the domain of the Chas-Sullivan loop product, which I will denote by dots. And one can justify these assumptions at the level of homology. Namely, we can always approximate homology classes such that they intersect transversally, and this product is well defined. This is the Chas-Sullivan loop product and the homology of the free loop space of a manifold. Okay?
I'm confused that for
Yeah.
circle you use manifold with curve only. This would maybe something like coproduct, not homology.
Yeah, yes, right now I'm not being precise in this sense. I'm just saying, let's think of a homology class represented by a map from a manifold with corners to the target.
You need more complicated objects than manifold with curve.
Ye-
But you can have trains in general relative position also, but you cannot insist on manifold.
Yes, you need more complicated. Yeah, you definitely need more complicated objects. But I'm just saying, in order to think of this transversality process here and obtain the inverse image for it to be a geometric object, I'm going to assume that it's a manifold with corners, just for the picture of the operation. Okay? But you can justify it using singular chains, for example, of course. Okay.
No, don't you have problem of
Orientation where?
of M, for instance, in which you take to intersect them?
M is oriented.
Sorry?
M is oriented. Yeah, yeah. M is oriented. Yeah. Close oriented manifold.
And the product could change sign if you change the orientation of M.
Yes, potentially. Yeah. Definitely. Yeah. Then one can prove that this product depends on the fundamental class, on the choice of fundamental class for M. Yeah. Okay. Now there's another operation which will play a role today, and it's a coproduct originally described by Goretzky and Hingston. It was described using Morse theory, but I'm going to give also a geometric picture like along these lines in order to have a good picture of how the intersection works. This is a coproduct in the homology of the free loop space of a manifold, but now I have an anomaly in the construction. So I have to kill the constant loops in order to obtain a well-defined map, as you will see from the construction. Okay, so let me give a picture for this coproduct. this coproduct, so this loop product is of degree minus k. This coproduct will now be of degree 1 minus k. And it's described as follows. Let's say I start with an I chain in your free loop space, and I'm going to think about this loosely as a map from a manifold with corners into the free loop space of a manifold. I want to consider self-intersections of loops, all possible self-intersections of loops, intersect at these, and then split into two loops. So what do I mean by this? I consider the following map to M cross M. Maybe let's call it E phi. E phi takes a point x in your domain chain and a parameter t, and evaluates the loop at x. For every x I have a loop at 0 and at your given parameter t. Okay? And now I want to consider self-intersections. That means I want to intersect this map with the diagonal. Okay? And potentially, I want to take the inverse image of the diagonal along this E phi map and obtain a domain here, Q. And so what's a point in Q? A point in Q is x and t are in Q, and you have a self-intersection, right? So for every x in Q, you have a loop phi x and a self-intersection at x, and I want to split into two loops at this self-intersection point. So I get v phi. We'll take a point in Q, and we'll split loop at self-intersections. Okay? So that's the idea behind the Goreski-Hingson coproduct. So there are several subtleties here, right? First, this construction is not a chain map, right? Because I added some new boundary here. I started with a chain, and I crossed with an interval which has new boundary, right? However, what happens at the boundary points 0 and 1? The images of these loops are constant loops in your manifold. Okay? So I get a chain map if I work in relative chains modulo constant loops. Okay? Second subtlety here is the transversality assumption. The deformation that I have to make in order for this map to be transversal to the diagonal, right? In particular, if we look at point 0 or u cross 1, this map will never be transversal, right? In fact, in the set theoretic image of the diagonal, you will always contain u cross 0 and u cross 1, because you always have a self-intersection at 0 and 1. Okay? So how do you deal with this transversality subtlety? Where, well, you consider the map E phi circle restricted to the open interval. You achieve transversality there. That can be done. And then you achieve transversality in such a way that the closure, let's put, this is the diagonal in M cross M. You achieve transversality in such a way that the closure with respect to the interval is a good geometric object, meaning it's a manifold with corners. Okay? So you have to, it's not only achieve transversality in the inside, it's achieve it in such a way that you control the closure of this submanifold. Okay? And that can be done. Okay? So these are the main constructions that will motivate the algebraic constructions that we'll discuss today. Okay? Any questions? Okay. Okay. So, okay.
So if this
Yeah.
kind of manifold is corner and it, you have where you have this equality. So what do you need about orientation? How do you get some orientation of this kind of covering?
You mean an orientation of
The space of an element of u plus d for which one has.
U plus D? Sorry? U?
No,
Uh-huh.
you get some family of loops, and
Uh-huh.
above it you have a new family of loops. Now you started with a family with an orientation. What do you need to orient the family you have above it?
So,
to have a side?
sorry, so what's the family that you're considering above here?
Yes, so this Q.
Q.
So how do you orient Q?
So U is oriented,
Yes.
right? So the inverse image here will have an induced orientation.
Yes.
So that's the orientation. No, Q is the inverse image of the diagonal, right? So that should have an induced orientation if U is oriented. Yeah. Okay. Yeah. Yeah, assuming transversality. So, in order to work these transversality out, I've worked together with Dingyu Yang a setting in which it's convenient, a convenient setting in which we can explicitly control, for example, these closures and obtain good geometric objects. And that setting is called the Ram chains. So I will mention the idea here, and then I will jump into the algebraic constructions that are analog to these operations. So what do I mean by the Ram chains? The idea here is to consider geometric chains on a space, and we're going to also consider as part of your chain a compactly supported differential form on your domain. Okay? So what you think of this as the cap product of your geometric chain and the Ram cochain. Okay? And this is convenient for transversality because now if I have a chain which is not transversal, what I do is I thicken my domain, meaning I take a bundle over my domain such that when I move along the fiber, I achieve transversality, the desired transversal condition that I want. And then this new space that I added, I kill by wedging with the Tom form. Okay? And this is a convenient setting to achieve transversality for string topology. It was proposed originally by Fukaya, actually in this string topology context for the product, for the loop product. Okay, but allowing corners in your domain lets you take care of constructions like the coproduct, where you're crossing by something that has boundary. Okay.
So this is good for real coefficients.
Real coefficients. No, I agree. Yeah. Maybe one can work with rational coefficients using some kind of rational forms, and yeah. And so theorem, which is part of work in progress, together with Yang, is that the Ram chain complex, which I'm going to call C of Lm, let's say modulo M, has a co-A infinity structure lifting the Goretzky-Hingston coproducts, this construction that I described. Okay? So the idea is to include into the operation the required deformation of transversality. But when we do this, we destroy any possible co-associativity that we have. But then you can show that up to coherent homotopy, you still have co-associativity. And these structures are, there's more structure here. This coproduct leads to a co-L infinity structure. There's also a co-BV algebra in the homology, in the Ram homology, let's say.
You lose unitality.
Sorry?
You lose unitality.
You lose unitality, that's true. When you kill the constant loops, definitely, because the fundamental classes, yeah. And potentially there's also this structure together with the loop product should induce NIBL infinity. This is a Lebye algebra, involutive Lebye algebra up to coherent homotopy in an S1 equivariant setting. So S1 equivariant chains. This structure should be induced by the product and the coproduct and the compatibilities with the BV operator, which is given by rotation of loops. Okay?
Could you explain to
Yeah.
me for associativity?
Co-associativity? Yes. So, so first of all, that a diagonal map to be able to split these complexes, right? But there's no natural diagonal map here. You can see in the way we've defined it. However, you can still make sense of the same equations for a co-associativity, right? Which have the form this is the identity map. Did I get this right? Yes. These are, yeah. So V is a map. Yeah, V should be a map. Right? But again, we don't have a we don't have a diagonal map, so this is the range and domain of the maps. Union. Okay. But we can still make sense of this map because of the construction has been described at the chain level. So you can still, maybe we should put this in quotes because it's not really crossed. But you can still make sense of this map, and this equation will not hold strict at the chain level. That's what I mean. But it will hold up to homotopy at the chain level.
Geometric picture. So the picture is when you have some loop with two.
Yeah, so the geometric picture, you have some loop, right, with a self-intersection, but now you're considering self-intersections in all possible self-intersections in the second loop, right? So it will look something like that, right? And the other picture will also look something like that, okay? So yeah, so this is all I wanted to say for the geometric motivation, and now I want to start discussing a algebraic theory for these operations in terms of Hochschild complexes, okay? And there I will describe how these two products, the algebraic analog of these two products, fit together, okay? Or some kind of duality between these two products, okay? In one product you're intersecting and concatenating, in the other you're splitting in all possible ways. So feels like there should be some kind of duality, but it's tricky to state, actually. Okay, so
Can I ask,
yeah.
Is this algebraic structure something that's a property of some class of topological field theories?
Which,
You know,
actually?
This co-A infinity, co-dv and all that.
Well, the product, the first one that I described, is part of a topological quantum field theory, right? The second one is not quite part of that same topological quantum field theory, actually, but it's believed to be associated to an action of the certain compactification of the moduli space. Okay. This is really, yeah. So that's all I can say. It's not part of the TQFT, actually, but it's related to.
Like, will you always get this on the Hochschild homology of a Coletti algebra?
Yeah, that's what I'm going to do now. Okay. So, okay. So let's move into the algebraic world. So A will be a differential graded algebra. So you can think of this, maybe think for now, as differential forms in your manifold with the wedge product. I will assume A is augmented. Let's say a DGA over R. So this augmentation you can think of as a choice of base point for M, right? And the given, some more notation. The kernel of the augmentation I will denote by A bar, and I will denote shifts on your algebra by S. So this means that the I minus 1 part here is the ith part here. Did I get that right? Yeah. Okay. So associated to any DGA, we have we can construct the Hochschild chain complex or the Hochschild cochain complex, and these are related to loop spaces by the work of Jones, by Chen, and so on. So Hochschild chain complex. So some notation, I'm going to, it's a double complex because your algebra is graded. So I'm going to use negative gradings for the first grading and positive for the second one. So CP of A, I mean the vector space. You take the augmentation ideal, you shift, you tensor it with it p times, and then tensor with A. So these are the total degree n monomials in this tensor product. Okay. And of course, I'm going to denote by dot the direct sum of these. And by Cn, I mean total degree n elements in the tensor, the whole tensor algebra, right? Tensor A. Okay. So I have the Hochschild chains differential, which using this convention, it will go degree 1 up. Yeah. Does anyone want me to write a formula for this, or no? Good. Yeah. And it's a theorem of Chen. Also follows from Jones. Or maybe I'm missing some names, but that if the manifold is simply connected, and if A is the differential forms in your manifold, then we have a quasi-isomorphism between Hochschild chains, the Hochschild chain complex, and in this case, the real cochains on the free loop space of M. This is a quasi-iso. Okay. Questions?
What is A?
A here is differential forms on M. Okay.
So you don't need to pass to a model which is connected.
It will be quasi-isomorphic. Yes. If M is connected, then you mean a model A?
Yes.
Yeah.
Yes.
If M is connected, you can take a quasi-isomorphic model, which is connected, and use that model here. But Hochschild chains are invariant under quasi-isomorphism. So. Wait, all this here. So the idea is that we want to recover this string topology operations at the level of Hochschild chains. Okay.
For any bit V.
What?
For any bit V.
For any?
Differential graded algebra.
But we need more data, right? Because the string topology used the Poincare duality of the manifold. So we have to include the data of Poincare duality. So we also have the Hochschild cochain complex, which will be relevant, right? And I'm going to denote it CPN of A. So this is, of course, this was known before all this loop space business. And I will use similar notation for the total degree and so on, right? These are,
I'm a little confused.
yep.
I was thinking that Chen was to get the common V of the loop space, not the free loop space.
Yes, Chen. Yeah, this follows from that fact of Chen, right? Chen proved that the bar construction of the DGA-A through iterated integrals is quasi-isomorphic to the cochains on the base loop space, right? But you can use this fact to prove that. Yes, in fact, he proved it, but he didn't call it the Hochschild chain complex. But he had the complex, yeah.
And
So.
Are you sure you want to take cochains on loop space and not chains?
Yes, I want to take cochains. Yes, that's why I graded these things in that way. Yeah, even if it's called Hochschild chains, note that the degree here will be going up 1. Or I could also grade cochains negatively and change the conventions here. But I want to take cochains. Yeah. Yeah. So you also have a Hochschild cochains, right? And here, it's been proven by, this is more recent, because I'm going to make a statement about the string topology operations by Tradler, maybe Menici, maybe Ralph Cohen. That so this Hochschild cochains have a coproduct, right? The classical Hochschild coproduct, and the result here is that there is a quasi-isomorphism between Hochschild cochains, maybe for simply connected manifolds. There is a quasi-iso of DGAs. This is the Hochschild. Now this is chains on the free loop space with the Chas-Sullivan loop product. Yeah. Okay. Note that this quasi-iso uses Poincare duality. In particular, there should be a shift here by K, where K is the dimension of the manifold. Okay? Because this cup product here is defined for any DGA. So I didn't use any Poincare duality for the underlying algebra A. So in order to relate that to the free loop space, the map uses Poincare duality. Okay, so this uses Poincare duality. Okay, good.
So this is when A is the differential forms?
This is when A is, yes, A differential form. Or cochains in the manifold as well. Yeah. Okay. So, yeah.
Is there maybe when you don't assume a manifold?
Good question. When you
don't assume
for this side,
Yes.
I don't know. I don't have a topological interpretation. That's a great question. Yeah. This is related to deformations of algebras, right? The Lie structure in Hochschild. So maybe one can think of what does it mean to deform the wedge product formally? Maybe that has a geometric interpretation. Okay, so in order to recover further string topology operations in these Hochschild complexes, it's convenient to have Poincare duality in your algebra holding strictly. Okay? That's a big assumption. Okay? But it can be justified. And I will explain why, or the result. So from now on, I'm going to consider differential graded Frobenius algebras. Okay? So I'm making a leap from differential forms to now these objects which have Poincare duality holding strict at the chain level. What does that mean? First, let me define a differential graded Frobenius algebra. So A D dot is a differential graded associative algebra. The pairing, these brackets define a pairing. Let me say of degree k. It means that this pairing is of degree minus k. The pairing, I will assume, non-degeneracy for the pairing at the chain level, okay, before passing to cohomology, which does not hold for differential forms, right? Now,
It agree with you want something finite dimensional?
yes, finite dimensional.
Intuitively to the Ham complex.
Exactly.
Proves, but it's
No,
infinite
but now I'm going to
dimensional.
assume finite dimensionality, and yeah. I'm going to assume the pairing is compatible with the differential. So the pairing passes to cohomology, and the Frobenius compatibility that it's compatible with the product, right? In that way.
So when you say DGA, did you assume commutative?
I'm not assuming commutative now. No. The structures that I'm going to describe work for non-commutative algebras, okay? And I'm going to be careful about that. I'm going to say that there are certain subtleties, okay? So I will go back to that point. Okay, so in particular, if you have such an object, you can get a coproduct, right? By dualizing the product using Poincare duality and using the finite dimensionality of A, right? You can get a coproduct, maybe I'll call it delta. You can get a coproduct using the isomorphism given by the non-degeneracy, applying the dual of the product using finite dimensionality. A check means the linear dual, okay?
So your formula for DAB equals ABB is up to some sign?
Yes, up to some sign. So yeah, I will be sloppy with the signs, okay? So from this data, we get a coproduct, right? And this coproduct is a map of DG A by modules. It follows from this compatibility, right? Okay.
No, do you have some assumption on degrees also? Is it bounded?
In our examples, they will be bounded, okay? But the
Positive degree?
positive degree, yeah, and bounded, both sides bounded. So, yeah. I want to keep this here up. Okay. So there's a theorem of Pascal Lambrecht and Don Stanley, an algebraic result, which says that any simply connected manifold can be modeled by such an object. Okay, so let me write, and that justifies my assumption that I can choose such a model for every manifold and study Hochschild complexes of these, and these are modeling string topology. Okay, so let me just state that this is Lambrecht and Stanley, and it's an algebraic result. Okay, so
Intuitively, one is able to replace the Ham complex by something smaller.
sorry,
It's essentially replacing the Ham complex
by something smaller, which has Poincare duality.
Yes.
So it's like enriching the Sullivan models in rational homotopy theory with the extra structure of Poincare duality, holding at the chain level.
But Sullivan would be infinite to the Ham.
Right. But it's yes, but that's the first step in the construction of these things. Okay.
And is it important to be simply connected?
It's the proof uses simply connectivity for an induction. Yeah. So it's an algebraic proof. Yeah. So if M is simply connected, there exists a DG commutative Frobenius algebra in this case. Okay. CDGA Frobenius A such that A is quasi-isomorphic as a CDGA to the differential forms on M, and the isomorphism induced by this quasi-isomorphism is an isomorphism of Frobenius algebras. Okay? So
As it is algebraic, would H1 vanishing be enough?
sorry?
As it is an algebraic theorem,
Mm-hmm.
would H1 vanish?
H1 vanishing is the condition that they do. Yeah, I'm just stating it in this way. So you see that this is weaker than saying you have a quasi-isomorphism of homotopy Frobenius algebras at the chain level, right? It's a weaker statement. Just the induced isomorphism is one of Frobenius algebras. This is all I'm going to use, okay? Now that I have these objects, I'm going to study string topology operations in Hochschild complexes of these guys, of these models, and I'm going to use the strict Poincare duality to obtain the operations, the intersection type operations, and then I'm going to relate the loop product and the coproduct in a single package. Okay, how to think of these operations in a single package. So, good. Maybe I can continue here. So
is your definition of Frobenius finite dimensional or no?
this implies finite dimensionality.
I guess it depends what you call non-degenerate.
It depends what you call non-degenerate. I call non-degenerate that this map is an isomorphism. Yeah. Okay. Good. So remember we had this coproduct. Right? At the homology level, the Goreski-Hingston coproduct. So now, in terms of Hochschild chain complexes, since Hochschild chains computes cohomology of the free loop space, I should be able to model this with a product, okay? Because it's a dual operation, right? So you can define a product okay? You can define a product. Now A is a Frobenius DG Frobenius, A is a DG Frobenius algebra, okay? Which you can think of as a cohomological model for the manifold with Poincare duality at the chain level. Okay? One can define a product on A on the Hochschild chains on A, behaving in the same way as this as the dual of this coproduct. In particular, it will be if the Frobenius algebra is of dimension k, the dimension of this product will be k minus 1. Recall the dimension of this V is 1 minus k, as I defined it. In particular, this will not be a chain map. Remember that we had this construction that we had to kill constant loops in order to obtain a chain map. Okay? So I can give a formula for this product, and you can compute the failure of being a chain map and so on. I won't give a formula, maybe at the end, but I will. However, it is a chain map if I take a subcomplex of the Hochschild chains, which models the process of taking or working modulo constant loop on chains. Okay. However, this subcomplex is defined. The underlying vector spaces, those monomials in which the tensor part is of degree at least 1. However, this is not a subcomplex if I don't assume that A is let me say, this is a subcomplex if A is commutative. Okay, you can check that you have a miraculous cancellation when A is commutative. When A is not commutative, this is not a subcomplex, and I cannot make sense of an operation which is a chain map. Okay, so this is how I started to think about other ways of how to obtain a chain map in the non-commutative case.
Is
Okay.
A connected here?
Sorry?
Is A connected?
A is, yes, A is connected. A connected. And moreover, this theorem says that you can take A to be connected and simply connected in this strict sense. Yeah. So it's very strong. Yeah. Okay. So I don't want to assume commutativity and find other ways of modifying my complex to obtain a chain map. Okay. And this idea led to putting the product and the coproduct together. Okay. So. Okay. So, I'm going to consider now the following double complex. Okay. Again, A is still a Frobenius algebra, DG Frobenius algebra, non-commutative now. And I want to put Hochschild chains and Hochschild cochains in the same complex. Okay? Yeah.
What's the reason for wanting A not necessarily commutative? Is because you want to handle characteristic P also? Or
That was not my reason. My reason was namely that I think all of these string topology constructions exist for differential graded associative algebras without the commutativity condition. So if I have a new operation, it should be part of the same theory. Maybe a naive reason, but
and
yeah.
about the product and coproduct
Yeah.
you defined initially, what kind of commutativity property does one have?
Yeah. Both are commutative in homology.
Yes.
Okay. Both commutative and co-commutative. Good. So I'm going to consider the new double complex, which consists of Hochschild chains extended by Hochschild cochains. So what do I mean by that? So I have Hochschild chains. I have 2 degrees, again, because A is a graded algebra. Okay, this is A, right? 0 length Hochschild chains. And now, using the Frobenius property, I have a map gamma of degree minus k, where k is the dimension of the pairing, right? You should think of this map as maybe the Euler characteristic map, okay? If you're thinking of A as a model for cochains on a manifold. Let me explain. What's this map? How to define it? You apply the coproduct I defined first by dualizing the product using Poincare duality. So how do we think of this coproduct if A is a model for the manifold? This is a model for the dual of the intersection product, right? And then I apply the product of A, okay? So this is like, if you think of chains, this is like applying the diagonal and then intersecting, right? Which should give you the Euler characteristic of, yeah. So this is your connecting map.
So,
Yeah.
a quick question. So
Mm-hmm.
the algebraic here, right? Is it actually Frobenius, or is the pairing should be degenerate, right? Because for example, if you take like a sphere,
What do you mean by Frobenius? Compatibility with the product, or a statement about degeneracy or non-degeneracy?
Degeneracy is the form, right?
Yeah.
So for a sphere, right, the string topology is infinite, goes up in infinitely many degrees.
Yeah.
So it can't be self-dual.
Right, but this duality is for
And so you
yeah.
recover it, right, when you add these negative pieces, correct?
yeah,
Yes.
in some sense.
So on the top, you don't actually get a Frobenius algebra, you get like a degenerate Frobenius algebra.
On the top,
Sorry,
Wait.
on the top board.
top board,
C tilde is actually a degenerate Frobenius algebra.
I haven't made any statement about C tilde being Frobenius.
Oh, okay, so
A, only
sorry,
A, yeah.
never mind.
A is
Not
like,
A tilde,
no, A is the manifold, right? Like, so A is also the cochains, right? And I can check that using this map, you get a differential which squares 0, right?
I'm lost with the degree now.
Yep.
This gamma is of degree
K, right? This is of degree K. This is of degree 0. Okay,
Oh,
so
but still, it just okay.
yeah. So I'm going to shift this side by 1. In fact, not by 1. I'm going to shift it by 1 minus K. You'll see why. So I'm going to put a shift here, 1 minus K. Shift 1 minus K. Shift 1 minus K. Okay? Okay, so I have a few more minutes. I will state my last theorem, and that will be it, which is regarding the product and the coproduct in this complex. Okay, good. So you have a differential which squares 0. You have a coproduct on this side, right? Hochschild coproduct. And now you can put this product star, which models the dual of the Goretzky-Hingston coproduct, without any modification in the non-commutative case, and you can extend this product to an algebra on this extended complex. Okay? On the totalization of this extended complex even. So let me make that into a statement. So I'm going to call this double complex D of A. Actually, D of A, I call the totalization of that double complex. Okay? And the main statement is the following.
It's
Yeah.
double complex, which in one direction is infinite in both directions, but on a finite state only.
Because A is bounded, right? And the algebraic result, which puts the model of the loop product and the coproduct together, is the following. This together with Shengfeng Wang. So 1, there is a product which I'm going to call star, but this bold star. In this double complex that extends star on the side of Hochschild chains, cup on the side of Hochschild cochains, and cap. There's a cap product for certain Hochschild cochains and chains, satisfying certain degree restrictions, right? And moreover, and compatible with the differential of D, right? So it passes to homology. Moreover, on this side, the cup product is associative. On this side, the star product is associative. But when you mix terms, the associativity, the strict associativity at the chain level gets destroyed at the chain level, because now you have mixed terms. However, there is an A infinity algebra structure on D extending star. Okay? It's actually the M4, M5, and so on are 0. The only non-zero structure map is the associator. Okay? That's interesting, right? And moreover, and this is the statement that I view as some kind of duality between the product and coproduct, the A infinity structure on D is cyclically compatible with the following pairing on D induced by the pairing on A. So I have a pairing on D. Actually, I'm going to define it in terms of the these filtration parts. So I take a Hochschild cochain of these degrees and a Hochschild chain of these degrees, and I pair it in the following way. I have a Hochschild cochain and a Hochschild chain. Maybe I'll write it in this way. And I evaluate the first P in F, and I take the product with P plus 1, right, in A. So I take the this is the product in A. So this product is this A infinity structure is cyclically compatible with this this pairing induced by the pairing of A.
What does that mean?
Cyclically compatible means, for example, if M's are the structure maps of the A infinity algebra, that you can cyclically rotate these entries here. Yeah. Okay. And now the last statement. I still don't have a chain level statement for this, but it's an interesting question, kind of a Deligne type conjecture for the following structure, that the homology of D is a BV algebra whose product is star and BV operator extends Cohn's operator on the left-hand side of cochains. Okay? So, yeah, so this is the main statement. Let me say something here. In particular, this means that this pairing is cyclically compatible with the star product. So, this is in particular. So this is, it combines the algebraic model of the loops of the loop product together with the algebraic model of the coproduct in the same complex, and it shows this compatibility with the pairing induced by the Poincare duality of the underlying algebra. So I think that's what I wanted to state, and we can talk more if you're interested about it. Thank you for listening.